Welcome to one of the greatest stories in science. It is a tale of two brilliant ideas. Each one describes our universe with incredible accuracy. Together, they form the foundation of everything we know about the cosmos. On one side, we have a theory that paints a picture of the grand and the majestic. It deals with planets, stars, and entire galaxies. It explains the graceful dance of celestial bodies across the vast expanse of space. This is the world of the very large, a universe governed by elegant, sweeping laws that we can observe with our telescopes. It's a universe that feels almost intuitive, a cosmic ballet on a grand stage. On the other side, we have a theory of the minuscule and the strange. It is a world far removed from our everyday experience. This theory describes the building blocks of reality itself. It governs the behavior of atoms and the particles within them. Think of electrons, quarks, and photons, the fundamental constituents of matter and energy. This is the realm of the very small, a place where our classical intuition breaks down completely. Here, particles can be in multiple places at once, and reality seems to flicker in and out of existence. It is a bizarre, counterintuitive, yet astonishingly successful description of the subatomic world. These two great theories are the pillars of modern physics. The first is Albert Einstein's general theory of relativity. It is our best description of gravity and the large-scale structure of the universe. The second is quantum mechanics, the framework that explains the behavior of matter and energy at the atomic and subatomic levels. For nearly a century, these two theories have been our trusted guides. They have allowed us to make predictions of breathtaking precision and have fueled technological revolutions that have reshaped our world. The problem, and the central mystery of this story, is that these two pillars cannot stand together. In almost every situation, physicists only need to use one theory at a time, but in certain extreme corners of the universe, they must. And when they do, the two theories clash violently. They give us answers that make no sense, predictions that are simply impossible. This is the great conflict at the heart of modern physics. Let's think about what each theory tells us. General relativity, Einstein's masterpiece, reimagined our understanding of gravity. Isaac Newton saw gravity as a mysterious force, an invisible rope pulling objects towards each other. Einstein revealed something far more profound. He showed that massive objects don't pull on space-time, they bend it. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now, if you roll a small marble nearby, it will follow that curve, spiraling towards the bowling ball. That, in essence, is gravity. It is the geometry of space-time telling matter how to move. Quantum mechanics, on the other hand, describes a world built on probability and uncertainty. It tells us that on the smallest scales, nature is fuzzy. A particle like an electron doesn't have a definite position until we measure it. Before that, it exists in a cloud of possibilities, a wave of probability. The world of quantum mechanics is not smooth and continuous like Einstein's spacetime. Instead, it is lumpy and discrete. Energy comes in tiny packets or quanta. It's a world of jumps and jitters, where things happen in distinct steps rather than flowing smoothly from one state to another. This is a fundamentally different view of reality. The conflict arises when we try to describe situations where both theories must apply. We need both gravity and quantum mechanics to understand the universe at its most extreme. Consider the very beginning of the universe, the Big Bang. At that moment, the entire observable cosmos was compressed into a space smaller than an atom. It was incredibly dense and hot. To describe this, you need general relativity for the immense gravity and quantum mechanics for the tiny scale. When physicists try to combine their equations to model this state, the mathematics breaks down. Another place where these two worlds collide is at the heart of a black hole. According to general relativity, a black hole contains a singularity, a point of infinite density where the laws of physics as we know them cease to exist. This is a point where gravity becomes unimaginably strong over an infinitesimally small distance. Again, we need general relativity to describe the intense gravitational field, and we need quantum mechanics to describe what happens at that tiny subatomic point. Just like with the Big Bang, the two theories give incompatible answers. The smooth, continuous spacetime of relativity cannot handle the fuzzy, probabilistic nature of the quantum world. This fundamental disagreement tells us something profound. It signals that our understanding of the universe is incomplete. Both general relativity and quantum mechanics are brilliant, but they are likely approximations of a deeper, more fundamental theory. This undiscovered theory is often called quantum gravity. It would be the ultimate unification, a single framework that can describe all the forces of nature, from the smallest particles to the largest galaxies. Finding this theory is arguably the most important challenge in theoretical physics today. The search for quantum gravity is more than just an academic exercise to tidy up our equations. It is a quest to answer some of the deepest questions we can ask about our existence. What really happened at the Big Bang? What lies at the center of a black hole? Is space-time truly fundamental, or is it made of something else? A theory of quantum gravity could provide the answers. It would represent the next great leap in our understanding of the cosmos, potentially rewriting our picture of space, time, and reality itself. This is the story of that search, a journey to the very edge of human knowledge. For decades, some of the most brilliant minds on the planet have taken up this challenge. They are searching for a unified theory of quantum gravity. Let's first delve into the world of string theory. The central idea is deceptively simple and elegant. If you could zoom in on any fundamental particle, like an electron or a quark, you would not find a tiny zero-dimensional point. Instead, you would find a minuscule one-dimensional loop of vibrating energy. It is a tiny string. All the different particles we see in the universe are not different entities at all. They are just different musical notes played on these fundamental strings. Just as a violin string can vibrate at different frequencies to produce different notes, these cosmic strings can vibrate in different patterns. One pattern of vibration might manifest itself as an electron. A different pattern would appear to us as a photon. Another, a quark. This is a remarkable idea. It means that the rich diversity of particles that make up our world could all be unified into a single fundamental object. The laws of chemistry would be the harmonies of these strings, the laws of physics their melodies. It is a vision of cosmic elegance, a universe built not from hard billiard ball-like particles, but from the music of these vibrating filaments of energy. The real magic of string theory, and the reason it has so many followers, is that one of its vibrational modes corresponds perfectly to a particle with the properties of the graviton. This is the hypothetical quantum particle of gravity. In string theory, gravity is not an afterthought. It is an unavoidable consequence of the theory itself. However, this beautiful theory comes with some very strange baggage. For the mathematics to work, string theory requires the universe to have more than the 3 dimensions of space and one of time that we are familiar with. Now let's turn to the main rival loop, quantum gravity. This theory takes a more conservative, though no less radical approach. It doesn't postulate extra dimensions or that particles are secretly strings. Instead, it focuses directly on the nature of spacetime itself. It takes Einstein's general relativity, with its description of gravity as the curvature of spacetime, and applies the principles of quantum mechanics to it. It asks a simple question: what happens if spacetime, like energy and matter, is not continuous but is quantist? What if space and time themselves come in tiny, discrete packets? In loop quantum gravity, the smooth, continuous fabric of spacetime described by Einstein is just an illusion, an approximation that works well on large scales. At the ultimate microscopic level, the Planck scale, space is not a featureless void. Instead, it is a network, a web of interconnected, finite loops of gravitational field lines. These loops are the fundamental atoms of space. You cannot have a distance smaller than the size of one of these loops. You cannot have an area smaller than a single tile in this quantum fabric. Space itself is granular, like a digital image that looks smooth from a distance but is made of individual pixels up close. This pixelated view of spacetime has a remarkable consequence. It naturally tames the infinities that plague other attempts to combine gravity and quantum mechanics. Because there is a minimum possible size, a fundamental length, you can no longer have a point of infinite density or infinite curvature. Loop quantum gravity also offers a tantalizing picture of what might have happened at the Big Bang. Instead of the universe beginning from an infinitely dense singularity, the theory suggests a big bounce. Both string theory and loop quantum gravity offer compelling visions for a final theory, but both face significant hurdles. They operate at energy scales and distances that are far beyond the reach of our current technology. The Planck scale, where these quantum gravity effects are expected to become dominant, is trillions of times smaller than an atomic nucleus. Probing this realm directly with particle accelerators like the Large Hadron Collider is simply impossible. This makes finding direct experimental evidence to support or falsify these theories an immense challenge. Without data, they remain beautiful but speculative mathematical frameworks. Physicists are therefore searching for indirect ways to test these ideas. They are looking for subtle clues that might be hidden in the cosmos. The truth is, we are still in the early days of this quest. It is entirely possible that both string theory and loop quantum gravity are incorrect. They might be important stepping stones, but the final theory could be something completely different, something no one has yet imagined. So why does this all matter? Beyond the elegant mathematics and the esoteric debates between physicists, what is truly at stake in the quest for quantum gravity? The answer is simple: everything. The search for a unified theory is not just about tidying up our equations or solving a few cosmic puzzles. It is a quest to understand the very nature of reality at its deepest level. It forces us to ask the most fundamental questions imaginable. What are space and time? Are they the smooth, continuous background we experience, or are they something else entirely, an emergent property of a deeper quantum system? A successful theory of quantum gravity will provide the answer, potentially rewriting our most basic concepts of existence. This journey forces us to confront the origins of our own universe. Furthermore, understanding quantum gravity is essential for comprehending the ultimate fate of the universe. And it is crucial for understanding the nature of black holes, those enigmatic objects that push our current theories to their limits. While the primary motivations for seeking a theory of quantum gravity are deeply philosophical, the history of science teaches us that fundamental breakthroughs often lead to unimaginable technological revolutions. When physicists were developing quantum mechanics in the early 20th century, they were simply trying to understand the atom. They could not have foreseen that their work would lead to the transistor, the laser, microchips, and the entire digital age. The abstract equations that describe the behavior of electrons laid the foundation for the modern world. It is a powerful reminder that blue-sky research driven by pure curiosity can have immense practical consequences that are impossible to predict. In the same way, we cannot possibly know what technologies a theory of quantum gravity might unlock. However, the true value of this quest may not lie in any future gadgets or gizmos. The real stake is our own understanding. As a species, we are defined by our curiosity, our innate desire to explore, to question, and to comprehend the world around us. The search for quantum gravity is the ultimate expression of that human spirit. We have journeyed to the very frontiers of human knowledge. We have explored the two great pillars of modern physics: Einstein's general relativity, which masterfully describes the grand cosmic ballet of planets and galaxies, and quantum mechanics, our strange and powerful guide to the subatomic world. We have seen how these two magnificent theories, each a triumph in its own right, fail to speak the same language. They offer us two different, contradictory stories about the nature of our universe. One is a tale of smooth, predictable geometry, while the other speaks of lumpy, probabilistic chaos. This fundamental conflict is the greatest challenge facing physics today, a deep chasm in our understanding of reality. The quest to bridge this chasm, to find a unified theory of quantum gravity, is one of the most ambitious intellectual adventures ever undertaken. We have delved into the leading contenders, string theory and loop quantum gravity, each offering a radical new vision of the cosmos. String theory suggests that everything is made from tiny, vibrating threads of energy, with reality playing out a grand cosmic symphony in hidden extra dimensions. Loop quantum gravity proposes that spacetime itself is not continuous, but is woven from discrete, indivisible loops, creating a pixelated quantum fabric at the most fundamental level. These ideas are beautiful, profound, and still deeply speculative. This grand symphony of physics remains unfinished. We have the soaring melodies of relativity and the complex staccato rhythms of the quantum world, but we are still searching for the final movement that will bring them together in perfect harmony. The problem, as we have seen, is the lack of experimental signposts. The realm where quantum gravity reigns is one of unimaginably high energies and tiny distances, far beyond our current technological reach. Physicists are like explorers with a map of a new world, but without a ship to take them there. They must rely on mathematical consistency, elegance, and the faint hope of finding indirect clues from the cosmos. This search forces us to confront the biggest questions of all. What happened at the Big Bang? What lies inside a black hole? Are space and time fundamental, or are they emergent properties of something deeper? These are the questions that drive us forward. They represent the frontier of our curiosity, the point where science and philosophy meet. The answers, when they come, will not just fill a gap in our textbooks. They will fundamentally reshape our perception of the universe and our place within it, providing a new foundation for our understanding of everything that is, was, and ever will be. The journey towards a theory of quantum gravity is a testament to the persistent, unyielding nature of human curiosity. It is a story that has been unfolding for nearly a century, passed down through generations of scientists. From Einstein's initial discomfort with a probabilistic universe to Hawking's paradoxes about black holes, the path has been paved with profound insights and stubborn puzzles. Today, thousands of physicists around the world continue this work, collaborating and competing, driven by the shared goal of finding the ultimate laws of nature. It is a monumental, collective effort that stands as one of the great achievements of our species, regardless of the final outcome. We stand at a unique moment in the history of science. We have, for the first time, a clear view of the boundaries of our knowledge. We understand the domains where our current theories work perfectly, and we can pinpoint the exact places where they fail. This is not a sign of weakness, but of strength. It allows us to focus our efforts, to know precisely which questions we need to ask next. The search for quantum gravity is not a blind fumbling in the dark. It is a targeted expedition into a known unknown, a deliberate attempt to chart the territory that lies beyond our current horizons of understanding. While the practical applications of such a theory remain in the realm of distant speculation, the true reward is the knowledge itself. The desire to understand the universe is a fundamental part of what makes us human. It is the same drive that led our ancestors to map the stars and our greatest minds to uncover the laws of motion and energy. Completing this picture by uniting the forces of nature into a single, elegant framework would be a crowning achievement of the scientific endeavor. It would provide us with the ultimate guidebook to the cosmos, a final story of why the universe is the way it is. So, the quest continues. The path ahead is uncertain, and the challenges are immense. The final theory may be one of the current contenders, or it could be something so strange and new that no one has yet conceived of it. But what is certain is that we will keep searching. We will continue to build bigger experiments, peer deeper into the cosmos, and push the boundaries of our mathematics and our imagination. Because written into our DNA is a need to explore, to question, and to understand. And the mystery of quantum gravity is the greatest exploration of them all.